Question number 5. An electromagnetic wave in a vacuum has a wavelength of 8.4 times 10 to the power minus 6 meter. So the first question is, state the name of the principal region of the electromagnetic spectrum of the wave. You need to learn the wavelength ranges of this electromagnetic wave regions. So you may find out that the region would be infrared. Okay, so in this A part, the second question is, calculate the frequency in terahertz of the wave. So terahertz, which means that 10 to the power 12. Okay, so first you need to find out the frequency. So what will be the velocity formula? P is equal to F lambda. You may rearrange to find out frequency, which is equal to V over lambda. What will be the speed of this electromagnetic spectrum? As you know, it is constant, 3 times 10 to the power 8 divided by the wavelength is given 8.4 times 10 to the power minus 6, which is equal to 3.6 multiplied by 10 to the power 13 hertz. But this term is not in terms of terahertz because the power is 10 to the power 13. So if you are rearranging this, you will be getting 36 multiplied by 10 to the power 12 hertz. So this 10 to the power 12 stands for this tera, which means that in terms of terahertz, it is 36 terahertz. 36. Okay. Then the B part of this question is, an arrangement that uses a double slit to demonstrate the interference of light from a laser is shown in figure 5.1. So the wavelength, there is the double slit and the screen and the distance. Okay, the light from the laser has a wavelength of 6.2 times 10 to the power minus 7 meter and is incident normally on the slits. The separation of the two slits is A. The slits and screen are parallel and separated by a distance of 2.8 meter. An interference pattern of bright fringes and dark fringes is formed on the screen. The distance on the screen across 8 bright fringes is 22 millimeters. So this distance is 22 millimeter as illustrated in figure 5.2. okay, so there's 8 bright fringes, so you may find out the distance between 2 bright fringes, this distance, by dividing 22 by 8. So the value would be 2.75. So in terms of meter, it will be 10 to the power minus 3 meter, right? Okay, this will be in use in the next question, I guess. So the first part is, the light waves emerging from 2 slits are coherent. State what is meant by coherent. 2 sources are coherent when they emit waves that have a constant phase difference. Okay, so here the 2 slits are acting as the 2 sources and they are emitting the waves of constant phase difference. So the second part is, calculate the separation A of the slit. You may use the formula lambda is equal to AX over D to find out this A value. Okay, so you may rearrange. So you'll be getting A is equal to lambda D over X. So here the lambda stands for the wavelength and D is the distance between the double slit to the screen, and X is the distance between 2 bright fringes, okay, which we calculated before. Okay, so substitute the values as this 6.2 times 10 to the power minus 7 multiplied by 2.8 divided by 2.75 multiplied by 10 to the power minus 3. So the value of A would be 6.3 times 10 to the power minus 4 meter. This would be the slit width. So the C part of this question is, Fringe P is the central bright fringe of the interference pattern in B. Okay, fringe Q and fringe R are the nearest dark fringe and the nearest bright fringe respectively to the right of the fringe P as shown in the figure 5.2. Let's check the figure. PQR. Okay, this is how it is arranged. PQR. So this is a bright fringe. This is central one. Okay, please note this is the bright fringe, this is the dark one, and this is the nearest bright fringe. So the first question is, calculate the difference in the distances or the path difference from each slit to the center of the fringe Q. So here is that fringe. Okay, sorry, the slits. Here is the screen. So the center, here it is P, here it is Q, the dark one, here it is R. Okay, so the waves are coming in all direction and meeting at this point. So when these two are meeting, they are meeting on the opposite direction. So these two waves that is meeting at this point is having a phase difference and a path difference. The reason for the destructive interference happening at that point. So the destructive interference is happening at this position Q. That's why it is forming a dark fringe. For destructive interference, the path difference is an odd number of half wavelength, which means that the path difference must be n plus half of lambda. Okay, so here at this point there is no phase difference. The path difference would be 0, but here this is n lambda. The reason for the constructive interference is n lambda. Here it is n plus half lambda, right? Since it is the first, I mean the nearest dark fringe, the n value would be 0. Okay, the nearest one. So the path difference would be only lambda by 2, which is equal to the lambda value is already given, like 6.2 times 10 to the power minus 7 by 2, which is 3.1 times 10 to the power minus 7 meter. So this would be the path difference of these two waves, and that's the reason for the destructive interference on this position Q. State the phase difference between the light waves meeting at the center of fringe R. So on the fringe R is a bright fringe, which means that at this position R, there is a constructive interference happening there, right? So at this position P, there is a central bright fringe, which means that the waves that is interfering at the point would be having no phase difference. 0 would be the phase difference at this point. Okay, the two waves will be having a phase difference of 0. On the nearest, it will be 360. Okay, 0, the phase difference of this bright fringes would be 0 to pi. If the two waves are having a phase difference of 0, 2 pi or 4 pi, 6 pi, like even multiples of pi, then there is a constructive interference happening. So on the central fringe, the phase difference is 0. To the first order bright fringe or the nearest bright fringe, the phase difference would be 2 pi, which is 360 degree. Okay, so the next question number 6 is, a metal wire in a circuit has a length of 1.8 meter and a cross-sectional area of 1.5 times 10 to the power minus 6 meter square. The total number of free electrons or the charge carriers in the wire is 2.3 times 10 to the power 23. There is a current in the wire so that a charge of 172 coulomb moves past a fixed point in the wire in a time of 2.5 minutes. The A part of this question is, show that the number density of the free electrons in the wire is 8.5 times 10 to the power 28 meter raised to minus 3. Okay, so you need to find out the number density, right? Mass density is mass divided by volume. So number density is number divided by volume. Okay, number of electrons divided by the volume. So what is the number of electrons that it is having? It's already given 2.3. The number of free electrons is 2.3 times 10 to the power 23 divided by the volume. How to find out the volume? The area is given and the length is given, so please just multiply these two. 1.8 multiplied by 1.5 times 10 to the power minus 6, which is equal to 8.5 times 10 to the power 28. Since the number doesn't have any unit on the denominator, the unit will be meter cube, so it is meter raised to minus 3. Hence it is shown. Then the next question, the B part is calculate the average drift speed of the free electrons. So you need to use the formula. I is equal to NeVA. So here the N is the number density which we calculated in the previous question. E is the charge of that electron, you already know, and it will be given in this formula sheet. V is the average drift velocity which we need to find out, and A is the cross-sectional area, that's also given. Okay, so we can rearrange. So V is equal to I divided by NeA. Okay, you know these three values, but you don't know the I value, right? I is basically current, is charge over time. So what is the charge value here? 172 is the charge, the amount of charge that is passed at the fixed point, and the time is also given 2.5 minutes. But remember, current is the charge flown in 1 second, which means that you need to convert this minute into seconds. So you need to multiply it by 60. So the value you will be getting is 1.15 amperes. Okay, now you have all the values that you need, so please substitute. So you will be getting the drift velocity value as 5.6 times 10 to the power minus 5 meter per second. Question number 7. A battery of electromotive force EMF 9.6 voltage and negligible internal resistance is connected in series with two fixed resistors and a thermistor as shown in figure 7.1. So this is the figure given. The fixed resistors have resistances of 3400 ohms and 5800 ohms. The reading of on the voltmeter in the circuit is 6 voltage. The A part is calculate the current in the resistors of resistance of 5800 ohms. So the current passing on this resistor. Okay, this is what you need to find out. So what you do for finding that, you can use the KVL, which means that sum of EMFs around any loop in a circuit is equal to the sum of potential differences around the loop. So which loop you need to consider? We can consider this loop. Okay, this one, the first loop. Okay, so in this, what is the sum of EMF? There is only one EMF here, which is 9.6, which is equal to the potential difference. There is a potential drop on this voltmeter, which is 6 already given, plus the potential drop on this resistors, right? What you need to find out. So voltage formula is current multiplied by the resistance. So here is also current multiplied by the resistance value. Okay, so using this I times 5800 would be 9.6 minus 6, which is equal to 3.6. So I is equal to, the current is equal to 3.6 divided by 5800, which is equal to 6.2 multiplied by 10 to the power minus 4 amperes. So the current is 6.2 times 10 to the power minus 4. Okay, then the next question is calculate the resistance of the thermistor. Okay, so here you need to find out this resistance RT, the thermistor resistance. Here is also you may use the KVL, I mean Kirchhoff's second law, voltage law. So here which loop you need to consider? We can consider the whole loop, right? The second one, the whole loop you can consider. Okay, the second one. So here is also the sum of the EMF is the same as 9.6, and the voltage drop. Okay, on this line, is there any the current value? There is 3 resistors, right? 1, 2 and 3. Okay, so here one resistance is 6, the current value, anyways the voltage is equal to IR, right? V is equal to IR. So here the current is 6.2 times 10 to the power minus 4 multiplied by the sum of resistors 3400 plus 5800 plus the resistors that you need to find out. Okay, rearrange this formula and find out the R value. You will be getting 6.3 times 10 to the power 3 ohms. Okay, so this is the resistance of the thermistor. Then the next question, the C part. The initial energy stored in the battery is 2.6 times 10 to the power 4 joules. Assume that the EMFs of the battery is constant. Okay, determine the final energy stored in the battery after a charge of 330 coulomb has moved through it. Okay, so what is the energy? The initial energy is given, right? So if you're subtracting the initial energy from the energy that you lost, you will be getting the final energy. So for that, you need to consider the energy that you lost. So E is equal to QV is the formula. Q value is already given 330, and the voltage as it's given, the EMF battery of the battery is constant, it stays the same, which is 9.6. So you will be getting that value of energy lost as 3170 joules. So this is the energy lost. So what is the final energy stored? Final energy stored is equal to the initial value minus the energy lost, which is equal to 2.3 times 10 to the power 4 joules. So 2.3 times 10 to the power 4. Okay, then the D part. The environmental conditions change, causing an increase in the resistance of the thermistor. State whether there is a decrease, increase or no change to these quantities. Okay, so the first one is the temperature of the resistor. As you know, the temperature, if the temperature is increasing, the resistance of the thermistor will be decreasing. Okay, so here there is an increased value of resistance, which means that the temperature must have decreased. Okay, then the next one, the current in the thermistor. Okay, so as the resistance increases, the potential difference across it is also increases, as V is equal to IR. So the resistance increases, V is also increases. So as the voltage increases, will there be any current flow? No, that is also be decrease. Okay, then the third one, the potential difference across the resistor. As I told you, as the resistance increases, the voltage or the potential difference would be increasing. Okay, then the last question, question number 8. An isolated stationary nucleus X decays by emitting an alpha particle to form a nucleus Y. Okay, X is decaying to Y and emitting an alpha particle, which is having 2 proton and 4 mass number. Okay, The nucleus Y and nucleus Z are isotopes of the same element. So isotopes are those elements which are having the same proton number but different mass number. Okay, so the A part is, by comparing the number of protons, you need to compare the number of protons in each nucleus. State and explain whether the charge of nucleus Y is less than, greater than, or same as the charge of the first one, nucleus Z. Okay, so Y and Z are the isotope. So isotopes is having the same proton number, right? So the protons, the number of protons, the both nucleuses are the same. So hence the charge must be the same, right? Because here you are considering the nucleus. So nucleus is only having the proton and the neutron. So the only particle which is contributing to the charge is the proton only. The neutron number doesn't count for the charge. Okay, so you need to write Y and Z have equal number of protons, so they have the same charge. Then the second one, so the nucleus X, so Y and X, will they be having the same charge or not? So you know that the X nucleus is decayed into Y, right? So it has lost, the X nucleus has lost 2 protons to form the Y nucleus. So the X is having more number of protons comparing to Y, right? So Y is having, then the B part. Use the principle of conservation of momentum to explain why nucleus Y cannot be stationary immediately after the decay of nucleus X. Okay, so the nucleus X previously was not moving, right? It was stationary. The momentum before decay is 0, right? So after the decay also, the momentum must be 0, because there is always a conservation of momentum. So conservation of momentum is that the total momentum before collision is equal to total momentum after collision. So since the nucleus X, which was stationary previously, is having 0 momenta, so after the decay also the total momentum must be 0, which means that if it is this has decayed into an alpha particle and Y, the X, if the alpha particle is moving in this direction, the Y has to move in the opposite direction to conserve the momentum. So the particle cannot be stationary. So by this we finish this paper. Let's meet with another paper. Okay, see you all. Bye.